We're looking at chapter 18, acid-base equilibria. Before we even start talking about equilibria of acid and bases, we should do a review of acids and bases. So we kind of talked about acids and bases in Gen Chem 1 in aqueous solutions, but we'll review what we talked about there, looking at the differences in acids and bases, looking at how to name acids, and so on. So acids and bases have been around forever. Okay. Romans used nitric acid to etch into copper. They called it aqua fortis, which in Latin roughly translates to strong water. And the reason, the name strong water, well, I take water, I pour it on copper, nothing happens. I take this substance that looks like water, pour it onto copper, and it etches right into the copper. So what are we going to call it? It looks like water, but it's stronger, so we'll call it strong water. Okay. So their aqueous solutions are acids and bases, so they have to be dissolved in water. They look like water. You can't tell the difference, all right, by just looking at a bottle. When acids and bases react with each other, they cancel each other's properties out in something called neutralization. So here is a typical neutralization reaction. Okay, of a strong acid and a strong base. Now we're going to come back to this because I really want to talk about strong acids and strong bases and review that right now. All right, so there's two definitions or three definitions we're going to talk about acids and bases. Okay, and the first one's known as the classical definition or Arrhenius definition. And your book uses Arrhenius definition for acids and bases, also known as the classical, all right, definition. But this chapter uses, I think chapter 4 uses classical, and then this chapter uses Arrhenius. So what that definition entails is how I react with in water. Okay. So let's start with acids. The form of a general acid is HA, a hydrogen bonded to some anion. We're going to take that HA and we are going to add water. The reaction gives us the key component of the classical definition or Arrhenius definition of the creation of hydronium. So, the classical definition of an acid is that when it's placed into water, it creates hydronium. Hydronium is H3O+. So it's a water molecule with an extra hydrogen. The classical definition of a base, and here's the general form of a base in classical definition, where X is some metal that makes the hydroxide soluble in water. We add the water since it's the classical definition. And what's important here is that we dissociate in the water and create hydroxide in whatever our metal is. So the classical definition for a base says when I place my base into water, it dissociates into a metal and a hydroxide. So the examples of Arrhenius acids, any of them, HCl, H2SO4, HCN, as long as they're in water and they've created hydronium, they are a classical acid. Bases have to make the hydroxide part soluble, have to create hydroxide when it's in water, can't be a solid. So you're talking sodium, any group 1 hydroxide, ammonium hydroxide, calcium hydroxide, your bigger group 2s are soluble in water. Okay. So we have our first definition of acids and bases. Now, our next thing is, well, we got to classify our acids. There's 2 types of acids, okay? There's strong acids and there's weak acids, okay? Strong versus weak. Now, there's a lot more weak acids than there are strong acids. The other thing I want to point out, what strong and weak mean is a strong acid will completely dissociate. A strong acid will completely dissociate in water. Okay? Complete dissociate. A weak acid only partially breaks down. Okay? So what that means is if I have a concentration of an acid, if I have 1 molar of a strong acid, then I'm going to get out 1 molar H3O plus. Whatever the concentration of the strong acid is, since it all breaks down, completely dissociates, I'm going to get out that much hydronium. So for a strong acid, the concentration of the acid is equal to the concentration of hydronium that'll be made. A weak acid only partially dissociates. So the concentration of the acid doesn't tell me how much hydronium I'm going to make. I'm going to make a significantly less amount of hydronium as a weak acid. So if we want to write something like this, the concentration of the acid in a weak acid is greater than the concentration of hydronium that I'm going to make. Now that doesn't mean you could bathe in weak acids. Okay, all that means is that I don't get the most bang for my buck, but hydrofluoric acid is a weak acid and it's not fun to work around. Okay, acetic acid in high enough concentration, which is the acid that's in vinegar, but it's only in vinegar as a 5% amount, will burn your skin. Okay. So what are our strong acids? How could I tell the difference? Because that's going to be important in this chapter. Can I tell the difference between a strong and a weak acid? Well, again, there's less strong acids than weak acids. So if you learn your rules for your strong acids, if they don't follow these rules, then they have to be a weak acid. So strong acids, first thing, a hydrogen, what we call a hydrohalide, which means hydrogen bonded to a halogen. There is an exception. HF is not a strong acid. So remember, halogens are group 17, so HCl, HBr, and HI are all considered strong acids. HF is not part of that group. Has to deal with fluorine's electronegativity and wanting to donate that proton, or have that proton dissociate, I should say. So number 1 over here, hydrohalides. Number 2, oxoacids. That means they contain oxygen. But there's a special caveat with my oxoacids. There has to be 2 or more oxygen than hydrogen. So, examples: H2SO4, HNO3, HClO3, the difference between oxygen and hydrogen has to be 2 or more. 4 minus 2, 3 minus 1, 3 minus 1, if I'm going to be a strong acid. So what about my weak acids? Well, number 1 on the list is our exception with the hydrohalides. HF is a weak acid. What about my oxoacids? Okay. Oxoacids that don't follow the rule of 2 or more. So examples of that: H3PO4, HNO2, okay, where the number of oxygen is not 2 or more than the number of hydrogen. 4 minus 3 is 1, 2 minus 1 is 1. Our third: what if I'm not a halide and I'm not an oxoacid? Okay, so I don't follow either one of the strong acid rules, like H2S or HCN. And the last one is organic acids, which means they contain carbon. Our most famous is acetic acid, which in the Gen Chem way would be written like this: H3O2 aqueous. Acetate with the hydrogen. But usually your organic acids are written in the organic way, just so you get used to seeing it. COOH is the organic way of showing acetate. C2H3OO. So this right here is acetate. Here's the hydrogen that's attached to it. You see this COOH, no matter what's over here, you should know that that's an organic acid. Okay. All right, questions on how to tell a strong acid from a weak acid? by looking at them, because that's going to be important. What's also going to be important is being able to name them, see the name, and understand how to draw it out, or am I strong or am I weak? Okay, there's two ways of naming acids. We've got two groups. We've got our oxo acids and we have our non-oxo acids. Okay. So let's start with our non-oxo acids. HCl. Okay. As a gas. As a gas, HCl would be hydrogen chloride. However, when I put HCl into water and make it into an acid, if I don't contain oxygen, I need the prefix hydro. I take the root of the anion, chlor, and add ic acid. So, prefix hydro, root of the anion, ic acid. So HCN, hydro, CN is cyanide, cyan, and then ic acid. H2S, hydro, sulfur, ic acid. So hydrosulfuric acid. So if I don't contain oxygen, I need the prefix hydro. First, I've got to be in water. Then I need the prefix hydro. Then root of the anion, chlor. Then ic acid. So hydro, chlor, ic acid. Strong acid, weak acid, weak acid. Completely dissociates, partially dissociates, partially dissociates. Then we have the rule for our oxo acids. Let's take a look. Whoops. Get rid of that right there. Like so. If they don't have a symbol of aqueous, so this is hydrogen, or we could call it dihydrogen sulfate. Dihydrogen sulfite. If they are aqueous, here comes our name. And this is why you should be familiar with your polyatomics. Okay. If I contain oxygen, no hydro. No hydro prefix if I contain oxygen. I take the root of my polyatomic. Sulfur. Sulfur. If I am the 8, it becomes ic acid. 8 ic, I ate too much ic. If I'm the ite, my ending becomes ous. So, in the last example, H2S that was right here, that was hydrosulfuric acid, a weak acid. This is sulfuric acid, a strong acid that has a difference in 2. Sulfurous acid has a difference of 1. So, HNO3 as an aqueous versus HNO2 aqueous. HNO3, that's nitrate. This is nitric acid. HNO2, well, if this is nitrate, one less oxygen makes it nitrite, is nitrous acid. Again, one weak, one strong, and that's going to be important. Okay. So here's, all right, 4 different acids that look very similar to one another. These 2 down here are weak. These 2 up here are strong. Naming them, well, this is chlorate. So this is chloric acid. Well, if this is chlorate, one less oxygen, this is chlorite. So chlorous acid. Now, if I'm one more than the 8, I'm perchlorate. So this is known as perchloric. And one less than the ite is hypochlorite. So this is hypochlorous acid. Okay. Questions on naming my acids? Slides 19 and 20 will give you practice on naming acids. Okay. So, when we're talking about acids and their strength, we're talking about how much breaks down. How much breaks down in water. So, we have a reaction. An acid plus water yields our hydronium plus whatever our anion is. Okay. Now, if I wanted to write a QC for this reaction, concentration of products, concentration of H3O plus concentration of A minus over the concentration of HA stay consistent over the concentration of water. Products over reactants. The thing is that when my acid breaks down in water, yes, we're going to get some of the water turned over to H3O plus. But the majority of my water, this change in concentration of water is very, very, very small. It's almost negligible. So we really don't use QC for acids and bases. For acids, we use something known as Ka. Ka standing for the dissociation constant of an acid. Okay. How much of the acid breaks down? And it's essentially the QC without the water. It's the concentration of hydronium times the concentration of A minus all over the concentration of the original acid. You are 100% right, Kelly. That's what I was getting to. You got it. So number one, it's a liquid, and number two, it doesn't completely change. The amount that breaks down is super, super, super small. So we take that out right away. It's not a gas, it's not aqueous, so it can't be in there anyway. So we call it the dissociation constant of an acid. Now, if I'm a strong acid, all of it is going to break down. I'm not going to have a denominator. So, if I don't have a denominator, my value is going to be greater than 1. So the Ka for a strong acid is going to always be greater than 1. The Ka for a weak acid, that's a terrible W, is going to be less than 1 because for a weak acid, this number is going to be bigger. Okay? So for a weak acid, the denominator is going to be bigger for my Ka, so I'm going to be less than 1. For a strong acid, I'm not even going to have a denominator. And you could actually see, and we'll show it, I have it here right out of the book. So, a strong acid, before dissociation, I have all strong acid. And it's going to break down into H3O plus and A minus. It's going to all break down. After dissociation, if I'm really a strong acid, I should have nothing in this column. So if we go back to here, if I don't have any of this at the end of the dissociation, my number is going to be bigger than 1. For a weak acid, I start with a large amount of weak acid, and after dissociation, I barely changed. I barely change. I get a little H3O plus, I get a little A minus. So, very big number, very small number, small over big, and it's going to be less than 1. So, if I place a metal like zinc, and I'm really doing a redox reaction here, but if I place it in a strong acid, 1 molar of it, and 1 molar of a weak acid, vinegar, acetic acid, okay, the acid that's found in vinegar, I should say, I'm going to get a lot more reaction over here because I have a lot more hydronium to react with the metal. And the reaction over here, I'm not going to get as strong as a reaction because I don't have enough hydronium, or a lot of hydronium, I should say, to react as violently over here. Yes, tannin, we have either completely dissociated and the reaction isn't going to occur anymore. We went to completion if a strong acid, or we reached equilibrium if I'm a weak acid with that Ka value. Yes, everything, if I look up the Ka of an acid, if it's a strong acid, the Ka value is completely dissociated, and for a weak acid, I'm at equilibrium where the max amount of that weak acid has dissociated. And this is everything that I just explained, and it's on the slides. Okay. Questions on that? Let's talk about bases. What makes a strong base a strong base? What makes it a weak base? Strong bases. A metal bonded to a hydroxide, a metal bonded to oxygen. Very simple. That makes it soluble. Weak base. The prime example of a weak base is usually ammonia or an organic substance where we replace one of the hydrogens, and this means carbon chain, we replace at least one of the hydrogens with a carbon chain, and we call this an amine. But there's a problem here. The classical definition said I'm a metal bonded to a hydroxide that when I place into water, I separate into hydroxy, or hydroxide, I should say. Well, ammonia doesn't follow that rule. Okay? Ammonia doesn't follow that rule. So the classical definition is incomplete when dealing with bases. It includes all acids, but it only includes my strong bases that have hydroxide to dissociate. It doesn't include this here, in theory, and it doesn't include ammonia, definitely. So we need a new definition for acids and bases that includes everything. And the guys to come up with that are these two right here. Bronsted-Lowery. And Bronsted-Lowery said, forget about looking at what I do in water and look at whether I am a proton or H plus transferer or I'm an H plus acceptor. If I am a H plus, a proton donator, I am an acid. And if I am an H plus acceptor, a proton acceptor, then I'm considered a base. Okay. So if I take an acid and I place it into water, we know that it should create hydronium. But how did I create hydronium? Water took that proton from the acid. This was a donator. So therefore, under Bronsted-Lowery conditions, I'm an acid also. I created hydronium by donating a proton to water. If we look down here, here's a general form of a base. You'll either see it as a B with two dots or a B with a negative charge. I'm a base. My base took a hydrogen from water. I am a proton acceptor. therefore I'm a base. I don't need just a hydroxide anymore. The classical definition said you needed to be a metal bonded to a hydroxide. Bronsted-Lowery says forget that. Do you have a lone pair? Do you have a negative charge? Can you accept a proton? That's all you need to be a proton acceptor. So things we would never think about, like F-, any of my anions. Okay, ammonia, like I said, because ammonia, if we draw out that Lewis structure, has a lone pair on it. Are all considered bases now, even though they don't follow the classical definition. So the rule of thumb is this. All classical acids are Bronsted-Lowery acids, because all classical acids will create hydronium. So there's the classical definition, and the way they do it is by donating a proton. So there's the Bronsted-Lowery definition. All classical bases okay, here's a classical base. Have hydroxide, which can be a proton acceptor. So all classical bases are Bronsted-Lowery bases. So all classical acids are Bronsted-Lowery acids. Period. If I'm an acid, I'm both. All Bronsted-Lowery bases or I should say all classical bases, let me correct that, are Bronsted-Lowery because they have the OH that could accept a proton. But all Bronsted-Lowery bases are not classical. And what we mean by that is F- is a Bronsted-Lowery base because it'll accept, but it doesn't have the OH-. Ammonia is a Bronsted-Lowery base because it'll accept, but it's not a classical because it does not have an OH. Okay? So all classical acids are Bronsted-Lowery. All classical bases are Bronsted-Lowery. But not all Bronsted-Lowery are classical, because we have things that'll accept that don't have the OH. Any questions on that? Those of you who had me for Gen Chem 1 heard that over and over again, because we kind of talked about this in Chapter 4. I don't know if Miss Lewis did, but if she didn't, that's fine, because it's supposed to be presented here. I just do it early just because, for completeness. So let's look at our friend water here. In our case here, water is accepting an H plus and turning into H3O plus. In here, it's losing it and becoming OH minus. So water's turning into this, water's turning into this. Here it's donating a proton. If I have a substance that can act like both an acid or a base, We say that it's amphoteric. Amphoteric means I can act like an acid or a base. Depending on the situation I'm placed in. Okay. Now, thanks to Bronsted-Lowery, we can now look at acid-base reactions a little bit different. So here's a reaction of H2S with NH3. So ammonia with hydrosulfuric acid. I know the AQs aren't there. Now, let's do this. This is a weak acid. Let's put a Q here. That's terrible. Okay. This is a strong base. Sorry, weak base, I should say. It's a weak base. Let me get my pen back here. All right. Weak base. Okay. This is, under Bronsted-Lowery conditions, going to donate a proton to this. And we get this product over here. I gave up a positive. Now I'm HS minus. I gained a positive, and now I'm ammonium. Now, if we look at this instead of left to right, we look at it right to left. HS minus turns into H2S. So over here, HS minus is acting like a weak base. And over here, NH4 plus is going to NH3. So NH4 plus is donating a proton and looking just like a weak acid. So my acid turned into a base, and my base turned into an acid. Well, this happens with every acid and every base. Okay. And we call these conjugate acid-base pairs. Every acid has a conjugate base, and every base has a conjugate acid. The acid becomes a base, the base becomes an acid just by doing the definition of an acid and a base. Okay. So, how do I tell, or how do I figure out what are my conjugate acid bases? Okay, so here you go. The conjugate base of an acid has one less hydrogens and one more negative charge. Or, if you want to stick with positives, the conjugate base of an acid has one less hydrogens and one less positive charge. So, H2S, one less hydrogen, one less positive charge. Became HS minus. If I'm a base, my conjugate acid has one more hydrogen and one more positive charge. So all my acids have a little bit of base in them when they donate their proton. They turn into one. Now the acid part takes precedent, but they do have a conjugate that goes with it. Okay. And this is showing essentially table 18.4. A whole bunch of different reactions. Identify what's your acid. Identify what's your base under Bronsted-Lowery conditions. So things that we would never consider being bases. CN-, water, carbonate, hydroxide. Okay, things that we wouldn't consider being bases are now bases. How do I tell on this one which one's the acid and which one's the base? Well, look at the products. This went down one hydrogen, so this donated to this here. This donated to this here. This is my acid. This is its conjugate base. This is my base. This is its conjugate acid. So, homework from the slides, besides slides, 19 and 20 for the naming of the acids, try sample problem 18.1. We'll talk about Lewis acids next time. Okay. So try sample problem 18.1. What was it? Slides 19 and 20, I believe. Yep, 19 and 20. So let me write down the homework because this is where I'm going to stop. Okay. What was sample problem 18.1, right? Yep, 18.1, which is slide 32. Let's do 19, 20, and 32. And then in the book, we're on page 834. Okay, 18.5 to 18.12. 1815 to 1818. 18. 18.41 to 18.52. Now, here's the homework. If you guys had me, these problems might look familiar. You did them when we did chapter 4. But I'm going to assume that you remember nothing. So we'll go back over them. So there's your homework for you. And we'll pick up with Lewis acids and pH in the next presentation.